Hi, welcome to class today. If you don't mind, grab a cutout on that table. We're going to use them later. Thank you. All right, class, let's get started. Today, we're looking at gas laws, the mathematical relationships among gas law variables, temperature, pressure, volume, and moles. Let's start by taking a look at today's objectives. There are 3 of them. First, you will work collaboratively to apply mathematical reasoning to deduce the relationships between and among the gas variables. Second, you will develop a hypothesis to explain the 2 gas law demonstrations you're going to see today. And lastly, you will design an experimental method to reverse the second demonstration. So how are we going to meet these lofty objectives for the day? Well, first, we're going to piggyback off that video lecture you watched at home. And we're going to do 4 things. Number 1, we're going to watch a demonstration involving candle and water, and you're going to hypothesize what you think occurred. Number 2, in collaborative groups, you're going to work through a POGL. You're going to analyze data and models and deduce mathematical algebraic relationships between the gas variables, temperature, pressure, number of moles, and volume. Then we're going to return and revisit that hypothesis you made. Do you still like it? Do you want to revise it? Do you want to make some changes? We're also going to share and have a short discussion on those observations. Lastly, you're going to watch a second demonstration that might help clarify things for you if you're still a little fuzzy on it. Individually, you will complete an exit ticket that will hypothesize that demonstration and propose a design, an experimental method to reverse it. Let's get going. So here's our demonstration. This is a plate of green colored water with a candle burning in the middle of it. I'm putting a glass over the top of it. And once the flame goes out, I want you to watch what happens at the bottom of the glass. Do you see the water rise? Remember those papers you picked up at the beginning of class? The first thing I want you to do is to stand up, take that piece of paper, and go find the people that make a picture with your piece. They're just old calendars cut up into pieces that do form pictures. Once you get into your new collaborative groups, get all your stuff, go sit together, and wait for instructions. Your first goal in your collaborative groups is to hypothesize why the water went into the jar. Think about when this occurred. Was the candle on? Was the candle off? Was that significant? Come up with a hypothesis. Write that down on paper. After that, I'll walk around and hand you out today's POGL. I want you to walk through the POGL together, analyze the data, analyze the models, and come up algebraic mathematical expressions that show the mathematical relationships between those gas variables. I'll walk around, I'll help out, I'll answer questions as necessary. If you don't understand something or you can't remember what an independent, dependent variable is, call me over and I'll come assist you. After that, we're going to talk about the POGL briefly, and then we're going to revisit that hypothesis. So number 1, hypothesize what caused the water to go into the glass. And number 2, work through that POGL, try to find the mathematical relationships amongst the variables. All right, so far we are being productive, and I have answered some questions. I hear some amazing things happening. But let's see where we are individually on understanding the gas laws. Each of you has an arrow at your table. I'm simply going to start a statement about the gas laws and the relationships, and I want you to either put your arrow up or arrow down, depending on what you think the relationship is. Are you ready? First, as temperature increases, volume. Good. As pressure decreases, volume. Okay. As the number of moles decreases, pressure. All right, nice job. Last one. As temperature decreases, the pressure. Good job. All right, from that little check, it's pretty obvious you guys are Doing awesome with the relationships between temperature and volume, number of moles and pressure, and temperature and pressure. They are all direct relationships. If one goes up, the other goes up. Some of you are still a little confused on volume and pressure. So I got a balloon. And I know it's kind of hard to see. It works really great with a large sponge that's kind of flexible. But right now, I'm kind of squeezing on this balloon, right? My question was, as pressure decreases, what do I need to do to decrease my pressure? I need to relax my hands. And when I do that, the volume goes up. So there's pressure, and if pressure decreases, the volume increases. Volume and pressure are the only two variables that have an inverse relationship. One goes up, the other goes down. Let's go back and revisit the hypothesis you wrote about why the water rushed into the jar. And let's go ahead and share a few ideas. Do we have any volunteers? Yes. We were thinking the reason the water goes into the jar is because the flame uses all the oxygen, and so there's no gas in the jar, and that leaves room, and the water can go in. Thank you for starting the discussion. Does anybody else want to add to that? Well, that's what we too thought. We thought that the oxygen was used up and there was all this room, and so the water just went into the jar. But then we remembered that a candle burning is combustion. So while the oxygen is getting used up, there's also carbon dioxide and water vapor being produced. So there's still gas in the jar. But we noticed that nothing happened until the flame went out. So we think when the flame went out, the air temperature went down, and low temperature causes low pressure. The molecules stop moving so much. So in the jar was low pressure, out here was high pressure, and it pushed the water into the jar. Yeah, at least that's what we think. I don't want to come right out and say who's right or who's wrong. I want you guys to think a little bit more. So let's watch one more demonstration. You ready? Now that you watch the egg get sucked into the flask, on your exit ticket by yourself, I want you to do two things. One, hypothesize. Why did the egg get sucked into the flask? And it must be based on the gas laws. Think about everything we've talked about today, everything you've read, the algebraic expressions you created. Then I want you to design a method to remove that egg based on the gas laws. But don't leave when you're done with your exit ticket. I want to sum up just real fast what we're going to start with next class period. Before you leave me, we are going to start our next class period using some of your designs that you turn in on your exit slip, and that is removing that egg from the flask without harming the egg. It's going to be a little bit like the flask giving birth. It's kind of fun. And then we're going to get into the gas laws a little bit further. Now, we've so far been talking about ideal gas behavior, how gases should behave. But just like people, gases don't always behave correctly. So we're going to actually look at the deviations from the ideal gas law. So everything we did today is going to carry on into our next class period. See you then.